First investigation what I'm going to do is I've been making videos for you and I'm not sure what to do. I've got 3 different color pens and I want you to be able to see them on the screen as well as possible. My hypothesis, my idea is that the black one would be most clear on the screen, but I don't know. So I'm going to do an investigation to test which you can see best on the screen. And all I'm going to do for each color, I'm just going to draw a little line. Okay, draw a line like that. There's my black, there's my red, there's my blue. And what I'm going to ask you to do is for those 3 colours, can you just give a score out of 10 for how well you can see them on the screen? Okay. Now I'm going to do it. I'm looking at the screen. I'm going to do that. I can see that black colour really clearly. I'm going to give that a 10. The red, I'm not so great with red. That's me. I'm a little bit colourblind. I'm going to give that a 4. That's just me. You might see it more clearly. I don't know. And the blue for me is somewhere in between. I'm going to give that an 8. Okay. There's my results. To me, black is the best one. Okay. Now, how have I've done my investigation. So what are my variables in this investigation? Right, well, let's have a little look. What I've done is the thing I have changed, right, I have changed is the color, red, blue, black. So my independent variable is the color. It's the thing I change, independent. What I've measured is how well you can see the color. Okay, and I've turned it into a number. I've said give us a number between 1 and 10, and that's what I've measured, how well you can see the color on a scale between 1 and 10. Okay, that's my discrete variable, my dependent variable. Okay, the dependent variable is the thing you measure. Okay, and the thing you measure here is how well you can see the color. That leaves the control variable. The control variables are things you keep the same because if you didn't, they'd affect the result. Okay, so my control variable, to make it fair here, look at my pens. I've used the same make of pen. It's the same type of pen. They've all got that medium point nib on, so the lines are the same thickness. Look at my whiteboard. I drew them all on the same color background. Okay, I used the same color background. So if I didn't, that would affect how well you could see it. The thickness of the nib and the quality of the ink will affect how well you can see it. I've kept them the same. Okay, the control variable is what you keep the same, because if you don't keep it the same, it'll affect your results. When you're asked to identify a control variable, don't just thoughtlessly say the things that could be the same, because unless they affect the result, they don't matter. They're not a control variable. They're not something you have to control. Quite often you get people say, yeah, use the same measuring cylinder. Well, does it make any difference which measuring cylinder you use, as long as it's the accurate scale, the appropriate scale? Okay, so think carefully about that. Right, let's have a look at our data. So if I was going to analyze this data, I've got my 3 colors there, and probably what I'd do is something like this. I'd do a graph. We like to do graphs, don't we? And I'd have black along the bottom. I'd have, what comes next? I'd do red, and let's do blue. Okay, so they're my 3 colors. And up the side, I'd have a scale, and the obvious thing would be to go 2, 4, 6, 8, 10, like that. And so 2, 4, 6, 8, 10. My black, I'll do a bar like that, 10. My red is like that, and my blue is like that, very rough, not very good at all. What this is, look at this data. The results are either for black, red, or blue. There's nothing in between. Okay, it's not a mix of colors. You can't be any color. You've got to be one of those 3 colors, and we call that discrete data. Okay, you're in one of these groups. Okay, so that is discrete data. Some of the data we'll look at later on isn't one thing or another. It can be within a range. It can be any number within a range, and that's continuous. But this is discrete. Look, black, red, blue. Okay, so independent variable, what I change, it's been the color. Okay, dependent variable, what I've measured, look, is the number, how well I can see it. And the control variable, how I've made it the same, is I've used the same pen, same nib, same background. Okay. So let's move. So we're going to be looking at another experiment now. Remember, independent, dependent, control variables, and continuous and discrete data. So if you can see my screen here, look, we've got a spring and we've got some masses. And my hypothesis, my idea, that is the bigger the mass, the greater the stretch of the spring. Okay, so simple experiment. Let's just have a little look at what we do. We put the mass on, the spring gets longer. Okay, I'm going to use a technical word. We're going to use the word extension. So if I stop the spring from swinging and I put a line in there, that was the length of the spring before I stretched it, and this is how much longer it's got, and I can measure the extension with my ruler. Okay, so the extension is how much longer the spring's got. So my hypothesis is the bigger the mass, the bigger the extension, and we're going to test that. So I can read the extension off on my ruler, and then I can put a different spring on, and there it goes, and then I'll stop it. Stop it if that didn't actually fully spring, did it? Let's get it going. Let's take it off and get it going again. If I stop it at the bottom position, let's say it's there. I didn't do that very well. And again, I can measure my extension, and then I can do that for my big mass here. And again, I could stop it at the there you go, resting position at the bottom, and I can measure that. Okay, so we're thinking about this not as an experiment with springs, but in terms of independent, dependent, and control variables. Okay, so let's go through. The independent variable is the thing I'm changing. So ask yourself, what am I changing each time? What am I changing each time? The dependent variable is what I'm measuring. What am I measuring each time? The control variables are the thing I'm keeping the same. What am I keeping the same? Okay, so have a pause and a think. So independent variable, what am I changing? Well, I'm changing the mass. No, I'm using these different masses. Okay, so the independent variable is the mass. The dependent variable, what I'm measuring, I'm using my ruler to measure the extension. Okay, and I put a pointer in to make that as accurate as possible. And I put a line in where the spring's at rest to make that as accurate as possible. And I bring my ruler up and measure it. So the dependent variable, what I'm measuring, is the extension. And look, I'm using a ruler that measured in millimeters, because that would make it accurate and give a good resolution and make it as accurate as possible. Okay, and the control variable or variables is what I'm keeping the same each time. And here, keeping the same spring. Okay, if I did it with a different, if I could use this, allows me to use a different strength of spring, and that would affect the reading if I use a different spring. Okay, so I use the same spring each time, and providing I don't stretch it past its limit, it will give me the same result each time. Okay, independent variable, what I change, I'm changing the mass. Okay, that one, or that one. Dependent variable, what I measure, measuring the extension. Control variables, what I'm keeping the same in this simple one, same spring. Okay. We're looking at another investigation here, and this investigation is to do with the pendulum. So this is a pendulum. You've got a mass on the bottom, this blue thing here with a 1 on, and you've got this bit of string here. And when I sort of pick up the pendulum, I can choose what angle to swing it from. Look, I've got my angle at the top. If I look, see that number at the top? Okay, and I can choose what angle to swing the pendulum from. Okay, I've got my stop clock here. Okay, and my stop clock measures the time. And what I'm going to do is I'm going to measure the time for a swing and figure out what is the time period for one swing. Now, it's a bit tricky to take this, get over there and start the stop clock and get it back in time. So I'm not going to measure the time for one swing. I'm going to measure the time for 5 swings. And if I want to know the time for one swing, I'll divide that number by 5. Okay, and that just makes it easier to, there's less of a percentage error when I go over here and start the stop clock. But my hypothesis is this: the bigger the angle I drop it from, okay, the longer the time to swing, the longer the time period, the time for one swing. Okay, and we're gonna test that. So what we're gonna do, we're gonna drop it from, I don't know, let's say minus 10 degrees to start with. I'm gonna measure the time for 5 swings. I'm gonna drop it from 20, measure the time for 5 swings, drop it from 30, measure the time for 5 swings. Okay, here we go. Just drop it from 10, and I'll get over there, quick scan. 1, 2, 3, 4, 5. Did I do that right? I think so. There's my time for 5 swings. Okay, and then I'd repeat that, and I'd lift it to -20. For the sake of example, I'll do the same. I'd measure 1, 2, 3, 4, 5, and so on. And I'll take the time, and then I'll go up to -30, and so on. Now, we're not fussed about what the results are. We're just looking at what the variables are. Okay, so independent, dependent control, independent what I change. The thing that I have changed, what have I changed? What have I measured? What have I kept the same? Have a little think. You pause the video, have a little think. Okay, so what I have changed, what I've changed is the angle I drop it from each time. Okay, I'm dropping it from 10 or 20 or 30, so I'm changing the angle. That's the independent variable. What I'm measuring, the dependent variable, is the time for, well, 5 swings, and then work out the time for one, but I'm measuring the time for a swing. Then what I'm keeping the same, the most important thing is to keep the same, the length of this pendulum, and use the same pivot. The length of the pendulum could easily affect the time for the swing, you'd think. The pivot, different pivots, where it rubs, it's probably got different amount of friction. It's important probably that that's the same. Okay, there could be other things. You wouldn't necessarily do it next to a window where there's a breeze and then in a still bit of the room, but the crucial thing here is the pivot, and the bit of string keeps the same. Okay, now we talked about continuous and discrete data. Okay, when I've doing this, I've got the time here. Now the time will be a number between 0 and, I don't know, probably 10 seconds maybe. Okay, but within that range, 0 to 10 seconds, it can be any number within that. It could be 1, 2, 3, 3.5, 4.25, 5 1/10, 5 1/1000th. It can be any number. And we call that continuous data. It can be any number within a range. Okay, the height of people in the class would be the same. Within a sensible range, you could be any height. You could be, 100 centimeters, 101, 102.5, 104.25. Okay, continuous data is when it can be any value within a range. Discrete data is when it's a choice of things. Have I got blue eyes, brown eyes, green eyes? It's a fixed choice. Okay, and that's the difference. This could be an example of discrete data. If I hang, I could either have 1 mass or 2 masses or 3 masses. Can't really have half a mass. Maybe, perhaps you could cut them up. Okay, but continuous can be any value. Discrete has to be one thing or another. Okay, so discrete and continuous data. Let's have a little look. We talked about in the pendulum investigation how the pendulum within a range could swing to any height. It could be any angle, and how the time isn't going to be either 1 second or 2 seconds. It can be any number between that range. Here's another look at some ideas about discrete and continuous data. So discrete data can only take certain individual values. So if you take up a book, it's got a number of pages in there. You don't have 1.3 pages. It's either page 1 or page 2. There's no page 1.5. If you look at shoe size, you're either size 6, 6.5, 7, 7.5. You don't have size 6.1 shoes. It's a fixed number of choices, and number of people in the Olympic sprint final. It's going to be 10 people. It's a fixed number. You don't have half a person. These things down this side, the even numbers, these are continuous variables. So if you watch 10 different films, they won't be exactly the same length of time. Okay, Star Wars was 2 hours 20 minutes. Different film, 2 hours 10 minutes, 2 hours 15 minutes. Within between probably most films, an hour and a half and 2.5 hours, they can be any number. It's continuous. It's not a fixed number. Your temperature, when you take temperature, My temperature is about 36.5 normally when I'm healthy. Could be 36.55, 54, could be 36. It can be any number. I'll be worried if it was less than 34, and I'll be very worried if it was more than 39, but within that range can be any number. And again, the time taken to run a race, let's say the 100 meters, world record's just under 9 seconds. A very slow person doing it would be, I don't know, 20 seconds. So within that range could be any time. You know, it's on someone's stop clock, could be any time at all, and that's continuous. So discrete, it can only be certain whole values, or certain values continuous within a range. It could be anything in between there. Okay, so it's learn to recognize the two things, and it's very important when you come to put it onto a graph. If on your x-axis, if that is discrete data, it's going to be a bar chart. Okay, if it's continuous data, you end up having a line graph. So you think about to the pens experiment, the color of the pens was discrete. It was one color or the other. I'm putting that on my x-axis, so it's a bar chart. The number you assign to how clearly you could see the line, that's continuous. You could have given any number, although you probably actually gave whole numbers rather than 1.3, but nonetheless you could have done. Okay.